All right, guys, so here 4.2, we're going to keep talking about probability. And now we're going to talk about some certain types of events. When we're looking at probability of events, there are independent events and there are dependent events. And whether they're independent or dependent has an effect on their probability if we were to combine them. Okay, when I say combine them, I mean these things here. We talked about this in the last section. This symbol with the upside down U means intersect, or the probability of A and B occurring at the exact same time. And the U shape stands for union. It means we're looking at the probability of A or B occurring at either time. Okay, so when we're looking at these combinations of probabilities, A and B or A or B, whether or not these two probabilities have effects on each other can change the way that we calculate them. So we're going to start talking about some formulas that we can use to kind of speed up this probability process so that we don't have to always have all the raw data to make a decision here about the probability. And the type of equation that we use is going to depend on the types of events we're looking at. All right, so events that have no outcomes in common are called mutually exclusive events. Okay, meaning if event A and event B are mutually exclusive, then the probability of them both occurring at the same time is 0, meaning they have no intersection. The Venn diagram would look like this, where the two circles do not overlap at all. There's no overlap. It would literally be impossible for them to occur at the same time. Okay, an easy way to talk about this is age. You can't be a freshman and a senior at the same time. It's not possible. So the events being a freshman and being a senior are mutually exclusive. Their intersection, the probability of A and B, is impossible. It's 0. The probability of A or B, though, would simply be the probability of event A occurring plus the probability of event B occurring. In other words, if I want the probability of A or B and I have mutually exclusive events, I just have to take everything in this circle and add it to everything in this circle, and I get the event of A or B. Super simple, right? But only if they're mutually exclusive. So let's look here. We have students on a hockey team. And we can see, based on the Venn diagram, that these are mutually exclusive events because these two circles do not overlap. So the event A and B has a probability of 0. It is impossible for somebody to be a freshman and a senior at the same time. The event A or B, though, would be the probability of event A, 2 out of, let's just say this is 4, 5, 6, 7, 8, total of 8 students here. So 2 out of 8 here, and we got 4 out of 8 here. So 2 out of 8 plus 4 out of 8 is 6 out of 8, or 3/4. So this general addition rule for probability, let's see. So up here, to get the A or B, if they are mutually exclusive, the probability of A or B would be just the sum of those two probabilities. Okay, so with this one, we just added them up. 2 8s plus 4 8s is 6 8s, or 3/4. Okay, now let's talk about what if they were not mutually exclusive. Okay, and it doesn't really say this in the notes, so let me kind of explain. So if I have two events that are not mutually exclusive, that would mean they do have an overlap. Okay, so this could be, let's go back to cats and dogs. Cats and dogs. Okay, in fact, I'll go back to the actual list of people we had in the first section, cats and dogs. Where's my cats and dogs? There they are. Okay, so if I wanted the probability of A or B, A union B, okay, in the last example, we said when they're mutually exclusive, I can just add those two probabilities together to get that combined probability. But what would happen if I did that here? The probability of A being a cat is 3 out of 5. The probability of B having a dog is also 3 out of 5. And when I add those two probabilities together, I get 6 out of 5. But wait a second, probability should never be bigger than 1. 6/5 is more than 1. So why do we get a probability greater than 1 when I follow that rule here? You should notice it's because I counted Nico and Zoe twice. The first time I counted Nico and Zoe was when I looked for the probability of having a cat, 3 out of 5. And then I counted Nico and Zoe a second time when I looked at the probability for having a dog and said it was also 3 out of 5. So I need to now stop counting Nico and Zoe twice. So I'm going to subtract this 2 out of 5 right here. So now instead of having Nico and Zoe counted twice, I should only have them counted once. We basically just subtracted that overlap. So that gives me back to 4 out of 5. 6/5 minus 2/5 is 4/5. Now look back, is that correct? Is the probability of A or B 2/5? Let's see, here's my area that represents A or B. I see 4 names, Roy, Nico, Zoe, Shay, out of 5, 4/5. So that's the general rule for probability of the intersection of two events. Okay, whether they're mutually exclusive or not, I'll go back to where I was. Whether they're mutually exclusive or not, if I want the probability of A union B, I can always do the probability of A plus the probability of B, and then subtract their intersection. So I'm not counting that overlap twice. And that will give me the probability of both, or one or the other. So this is our general rule for the probability of a union of two events. And this also does work for mutually exclusive. In mutually exclusive, this number would just be 0. Okay, so why do I need this formula? We just saw with the cat and dog thing, I can look at the Venn diagram and see that it was 4/5 without doing all that math, right? So the thing is, normally we have more than 5 people we're talking about. When we're doing probability, we don't look at just 5 people. We look at thousands of people and millions of people and huge amounts of data. And it's actually much, much easier in all probability cases to look at the numbers and not the raw data. So this equation here allows me to look at the numbers without having to sort through the raw data every time. So let's go ahead and do this example here. So we don't have any context to this problem, just the probabilities themselves. So the probability of event A is 0.3. The probability of event B is 0.5. And the probability of A intersect B, A and B, is 0.2. So what's the probability of A or B? Probability of A union B. So the probability of A or B, which can be written as the probability of A union B, remember both mean the same thing, is equal to the probability of A plus the probability of B minus the probability of A and B, their intersection. Okay, so I could rewrite this with the U notation as well. So these two equations mean the exact same thing. Okay, just written 2 different ways. All right, so let's go ahead and plug in the numbers though. Let's see, the probability of A was 0.3. The probability of B is 0.5. And then the probability of their intersection, so we can subtract off that overlap, is 0.2. I also know right away that these two events are not mutually exclusive. If these two events were mutually exclusive, then the probability of A and B would equal 0, not 20 or 0.20. Okay, so continuing here, go ahead and finish this off. 0.3 plus 0.5 is 0.8, minus 0.2 is 0.6. So the probability of A or B, the probability of A union B, is 0.6. Ta-da. All right. So on this one, we're actually going to use this equation up here that I highlighted to get another equation for the intersection rather than for the union. So basically, again, these equations are helpful for when we only have access to numbers and not data, or when the data is too large to count. So if I take that equation from the last one, probability of A or B equals a probability of A plus a probability of B minus a probability of A intersect B. Okay, I can manipulate this equation to instead get a formula for this probability. Okay, all I'm going to do, I'm going to go ahead and start by adding this probability to both sides of my equation. And then I'm going to subtract, here, I'll write that out first. So that gives me probability of A union B plus the probability of A intersect B equals the sum of the probabilities. And then subtract off this union part now. So I'm left with an equation for the intersection instead. So now my equation looks like this. The probability of A intersect B is equal to the probability of A plus the probability of B minus the probability of A union B. So this looks exactly like we had above, except for the union and the intersection kind of traded places. So that gives us another formula that we can use, again, when we don't have access to raw data. The probability of A intersect B is a probability of A plus a probability of B minus the probability of their union. Okay, so basically the union and the intersection have the same relationship. So let's go ahead and use that formula to calculate this combined probability. So the probability of A is 0.3, the probability of B is 0.4, the probability of A union B is 0.6. So what's the probability of A intersect B, which they give you the answer right there. Okay, we're going to get that answer though. Let's go ahead and work it out. The probability of A intersect B is the sum of the individual probabilities minus the other combinations. We had intersect here. I'll have union there. Okay, so again, this addition rule works either way. We'll just have opposite intersection and union in those two locations, either way. So I'll plug in what I have. Let's see, the probability of A intersect B is what we are solving for. The probability of A is 0.3. The probability of B is 0.4. And the probability of their union, is 0.6. So that's 0.3 plus 0.4 is 0.7, minus 0.6 is 0.1, which is exactly what they had over here. So remember, while you're doing your assignment today, if you have any questions, you can email me or jump on Zoom. I'll be here all day to help you. All right, moving on. Next thing here, talking about independent and dependent events. So if the occurrence of one event does not change the probability of another event, we say the two events are independent. Okay, so we can talk about rolling a die. If I roll a die and get a 3, does that change the probability of rolling the die a second time and getting a 5? No. The probability of rolling a die does not affect the probability of a second roll on that die. It doesn't make something any more or less likely than it was to begin with. We can also talk about grades in class. Does one person's grade affect another person's grade in class? No. Your grades are independent of each other. It all depends on you. If two events are not independent, though, we would say they are dependent. That would mean the occurrence of one event does change the probability of another event. So these two events would be dependent. So in other words, you would say you are more likely to slide into the ditch if it snows outside, or if it rains and snows outside. You are less likely to go in the ditch if the roads are dry. So since one event, the weather, has an effect on the probability of another event, you're driving, we would say that those two events are dependent on each other, okay? The likelihood of you going into the ditch while driving is dependent, at least partially, on the weather. So let's talk about independent and dependent events. So here's some more. It says event A is you get a 6 on the first roll of a number cube, and event B is you get a 6 on the second roll of a number cube. Do these events affect the probability of each other? No, they do not. No matter what you roll on the first roll, it's not going to affect your chances in the second roll unless you cheat and just don't roll it very well. So we would say these are independent events. Okay, next one. It says event A is it rains today. Event B is you bring an umbrella to school. Okay, I know most of you guys, even if it rains, probably won't bring an umbrella to school. But the point is, students, people in general, are more likely to bring an umbrella places if it's actually raining. You're less likely to grab an umbrella on the way out the door if it's not raining. So these two events would be dependent. Okay, let's look at this one. A bag has 4 gumballs. 1 is red, 3 are yellow. Your friend randomly chooses a gumball and keeps it, and then you randomly choose a gumball. So let event A be your friend chooses a red gumball, and event B be that you choose a red gumball. If your friend chooses a red gumball and keeps it, does that affect your chances of drawing a red gumball? Well, yeah, because there's 1 less red gumball in the bag. In fact, there's only 1 red gumball in the bag. So if your friend draws 1 red gumball and keeps it, there's no more red gumballs in the bag. So therefore, it would be impossible for you to draw a red gumball. Whereas before they took that red gumball out, you had a chance of getting it. So these are dependent events. If somebody takes something out of a bag and keeps it, the probability of drawing anything else out of that bag is going to be changed. All right, so now that we have a firm grasp on what independent and dependent events are, we can talk about combined probabilities, the ands and the ors, the intersects and the unions, based on whether or not events are independent or dependent. So if events are independent, then we actually end up with this other formula for the probability of their intersection. The probability of A intersect B, or A and B, is also equal to the probability of their product. Remember, this dot here means multiply. Okay, we can also use this rule in reverse. We can say if the probability of A and B is equal to the product of the individuals, then we know for sure that those two events are independent. Okay, so let's use this both ways. Here it says the probability of A is 0.4, the probability of B is 0.3, and it says here these are independent events. We won't talk about how to do this multiplication thing with dependent events until the next section. So what is the probability of A and B? Well, since they're independent, the probability of A and B should be equal to the probability of A times the probability of B, which is 0.4 times 0.3, which you can use a calculator, but 4 times 3 is 12, right? So 0.4 times 0.3 is 0.12. Okay, but you're welcome to use a calculator. Okay, next one. Again, we know these are independent events. It says so in the directions. So the probability of A and B is going to be the product of the individual probabilities. Event A has a 20% chance. Event B has a 25% chance. So if we multiply those, let's see, what's 25% of 2 or 0.2? That would be 0.05. Okay, so that would be it. Now, what if we want to use this the other way around? Now we're trying to determine, are these events A and B independent? It doesn't tell us, are they independent? If events A and B are independent, then the probability of their intersection should be equal to the individual probabilities multiplied together. Are they? Is 0.12 equal to 0.4 times 0.3? Yes, it is. So events A and B are independent because the probability of A and B is equal to the probability of A times the probability of B. All right, here. It says the probability that a random customer buys a book is 25%. So the probability of book is 25%, as a decimal is 0.25. The probability that a random customer buys a game is 50%. So the probability of game is 50%, as a decimal, which is 0.50. The probability that a random customer buys a book and a game and a book is 15%. So the probability of game and, I'll use the intersect symbol for and, book is 15%, which as a decimal is 0.15. So conclusion, buying a book and a game are they independent or dependent? Well, again, if they are independent, then the probability of the game intersect the book should be equal to the probability of buying a game times the probability of buying a book. Is that true? Is 0.15 equal to 0.5 times 0.25? What is a fourth of a half? That would be 1/8. I don't think that's 0.15, is it? 0.5 times 0.25. You can grab out a calculator and do that. You should get 0.125, which is not equal to 0.15. So these events are not independent. And if they're not independent, then they have to be dependent. And that's it for this section. Remember, there's one more section to do this week. We were going to do them both today, but since we have kind of a virtual week going on, I split it up for you. You're welcome to do it today still if you have time, or you can do it tomorrow. Get them all done this week though, and you get some extra credit. So make sure you get it done.